Yeah, so we stopped at, we were looking at the Yagi, and I hope everyone has seen a picture of it or you have seen it already. Okay, during the few hours, of course, you could have walked around your estate and you might have seen a Yagyuda. The Yagyuda you saw was that the active element is actually a folded one, and the issue of folding is so that you can improve the impedance. We have seen like that a dipole has a radiation resistance of about 73 ohms. Usually, the TV inlet input is usually a 75 ohm, and therefore you can see that the 75 ohm and the 23 ohm has a very low standing wave ratio or a very low reflection coefficient. But you find that air, that is free space, has an intrinsic impedance of 377 ohms, and therefore the antenna will be unmatched to its impedance, unmatched with the air, so to speak. And therefore, most of the time you want to improve the matching of the antenna and the medium surrounding it. And therefore, when you fold the dipole, you now have twice the current for the same. It's like you have an array of two elements, active elements, and therefore the impedance that you get for the radiation is that you are getting twice the power, and therefore the current is like it's 4 times, and therefore the impedance improves to about 300 ohms. And that's why you fold the dipole so that you get an equivalent two dipole element with a characteristic impedance that is very close on and radiation resistance that is close to that of the intrinsic impedance of the medium, and therefore you get a more efficient radiator. And that's why the TV antennas, you find that they all have a folded dipole active element. Now we look at what we talked about. We have seen that the dipole itself is a resonant length antenna. That is, the length has to be half lambda, or for a monopole, it has to be lambda by 4. And we know that this is a resonant length because the impedance of a transmission line that is quarter lambda long, if it's open circuited or it's whatever, it will be very high. That is, we get an infinite kind of open circuit at the input, so to speak. And therefore, these are usually very narrow band. That is, the frequency over which you can use it is usually narrow indeed, but it's a high Q element. Now, many of the times you may want to get an antenna can operate over many frequencies, because what would happen is that if you used a dipole to try and cover the radio spectrum, where you may start from about, say, for the FM from about 88 megahertz to about 108 megahertz, then you'll have to keep on tuning the length so that it's resonant at the center frequency of the transmitting radio or the radio station. And therefore, to cover the whole broadband or the whole band of the radio frequency or the FM spectrum, you will need an antenna that is not very resonant. And this is what we call a broadband antenna. So the pattern and impedance characteristic of an antenna will depend critically on its dimensions in terms of wavelengths at the operating frequency. So the antennas with similar geometric structures will hence retain the same radiation characteristics if the ratio of the antenna dimension to the wavelength is frequency independent. That is, you want to show that at every frequency, the ratio between the actual frequency that you're dealing with, or the wavelength you're dealing with, and the length of the antenna, that is L over lambda, remains constant throughout the frequency band. And in this way, the antenna dimensions will then be said to be scaled in wavelengths, and the direction, the radiation characteristic of the antenna will therefore be frequency independent. So one antenna that has this characteristic is what we call the equiangular spiral, which is defined by a radius of r equal to r naught multiplied by the exponent of a into phi minus delta, where we define r and phi as the usual polar coordinates, and r naught, a, and delta are the design constants for the antenna. So the spiral is equiangular in the sense that it makes the same angle with the radius vector at all points on the spiral. So the angular spiral antenna, also known as the logarithmic spiral, is shown here. This, if you recall your mathematics, is actually the curve, the spiral, the conu spiral, okay? And this is assumed to be infinitely long, but we can always truncate it at finite lengths. So the logarithmic nature of the spiral comes from the fact that the argument phi minus delta will be equal to 1 by a multiplied by the natural log of the ratio of r divided by r naught, where we have said that r naught, a, and delta are design parameters. So that, and those ones are the coordinate system parameters. So three design constants will determine the characteristic of the antenna, and these are the size of the termination region, that is how large the R node is at the termination where you are connecting your generator or where you are connecting the extraction point. And two, the reciprocal rate of the spiral, which is given by 1 by alpha or A, and the spiral arm width, which is the delta. So the four edges of the planar equiangular spiral are then defined by R equal to R naught, exponent of A alpha, or A multiplied by phi, R equal to R naught, exponent of A phi minus delta, and the other be phi minus pi, and the other one is phi minus pi minus delta. This gives the four edges of the spiral, of the spiral itself. So the operation of the antenna may be viewed as, one, the excitation of a voltage source at the antenna terminals will cause currents to flow outward until they get to a point on the spiral where most of the radiation will occur. That is where the length or the dimensions of the antenna become resonant. And this we see will be varying along the spiral as we change the frequency. So the electric field intensity vector between the spiral arms will be traveling outward until the arm separation is about a lambda by 2 at the operating frequency, and therefore strong radiation occurs. So currents will decay rapidly beyond the resonant region of the spiral, and the spiral can be truncated with little effect on the radiation characteristics. Of course, this also limits the band or the bandwidth of the antenna as well. So an increase or decrease in frequency will only shift the resonant region along the spiral. And the two-arm angular spiral radiates circularly polarized fields, and the radiation pattern will rotate about the axis normal to the spiral as frequency is changed. So the radiation is broadside rather, with major lobes on either side of the plane of the spiral, and this can be an advantage because we can get a backward reception of radiation, and this can cause ghosting if you are using this other reception antenna. So for the equiangular spiral to be truly frequency independent, then the spirals have to be ideally of infinite extent. So another form is what is given here as a logarithmic periodic, the log periodic antenna, which will be having a plate with teeth that are changing in length as we go out from the feeding point outward. This you can call it a biconical antenna, in which the conics have been given teeth of varying lengths. So the teeth present discontinuities that will tend to localize the region where the main radiation will occur and cause the current to diminish rapidly beyond this region. So the tooth lengths are determined by the angles between the lines from the origin, and the strongest radiation will occur where the tooth length is a quarter lambda. So the spacing between the successive edges of the teeth will follow the same rule governing distance between conductors in the equiangular spiral. That is, the Rn, the position of the next tooth to the previous one, that is Rn plus 1 over Rn, is going to be given by R naught exponent of A phi minus delta, R naught exponent of A into phi minus 2 pi delta, and we get a value of exponent of twice pi multiplied by the A, which is we said was a reciprocal whatever the pitch of the antenna, which is equal to given a symbol tau. And for a finite infinite structure, antennas characteristics will be identical at discrete frequencies, which are related to tau as f of n equal to tau multiplied by f n plus 1, giving us a ratio of the natural log of f of n plus 1 equal to the natural log of f of n plus the natural log of I of 1 over tau. So the planar log periodic antenna is bidirectional as well. That is, it will radiate both sides of its plane, like the equiangular antenna, and the main lobe will be broadside either side of the plane of the antenna. So the two arms of the antenna can be folded to form a wedge, okay, and this will make it unidirectional. That is, we fold them closer together, that is out of their plane, so that they form an edge. And therefore the radiation will be in the direction and of whatever. It will look like almost like a horn antenna without the side walls, so to speak. So the planar log periodic antenna without the teeth forms what we call the bow tie antenna, and with limited broadband characteristics, but usually this is useful, especially when you are for TV, UHF TV reception. Another log periodic antenna that you can see, especially if you walked towards the airport, or where if you go to, as you go into Mlolongo, there is a place where there is a station for the airport, where we have a reception, and you can see some of these antennas there. So the log periodic antenna can be realized with wire or tubes if the tube outline of the cutout, the design of the planar log antenna will be shown as here below. So the lengths of the different teeth are the ones which will be related in a log periodic way, that is ln over ln plus 1 is going to be equal to a constant. So here we are starting from this end, and we can see that this antenna can be operated in two ways, either feeding it from one end, the long end, and this one will be the reflector, or we can feed it from the other end here at the apex. This also assumes that the length or the triangular thing, that is, it's of infinite length in that direction for it to work really as frequency independent. So the dipole spacings and the lengths are in the ratio of ln plus 1 over ln equal to the spacing rn plus 1 over rn, which is equal to tau, where the tau will be the design parameter. And since the element spacing are related to the distances to an imaginary apex with the apex angle of alpha, we can therefore write that dn equal to rn minus rn plus 1, which is equal to rn into 1 minus tau. That is the spacing between the two teeth. So hence, the spacing of the dipoles, dn plus 1 by dn, is as well equal to tau. So the apex angle or spacing factor, which is gamma, is another important design parameter for these antennas, and it's given by gamma equal to dn divided by twice the length of the dipole. That is the whole dipole, this ln being the half length of the dipole, and the design parameters are then related through the tangent of alpha by 2, where the tangent is of course the apical angle, is equal to ln by 2rn, which is equal to ln into 1 minus tau over 2 dn, or we get a value of 1 minus tau over 4 gamma. And in the strict sense, the wire radius should be scaled as well as an plus 1 over an, which is equal to tau as well. And this is because we have been looking at the antennas and assuming that the wires are infinitesimally small, that is, the radii are very small, therefore we have filamentary radiation. But if the radius of the wire is different from 0, we can see that the current density around the wire, because of skin effect, will not be uniform throughout, and therefore the distribution of the current will change and therefore the radiation characteristic of the particular antenna will also change as well. But in many cases, we find this is usually a very small correction, and therefore we can always use the theoretical infinitesimally or filamentary current excited whatever antennas. So the log periodic dipole array will operate in an end fire with direction with the main lobe radiation directed toward the shorter dipole end. So in theory, the sheet thickness and wire diameter should increase linearly with the distance from the feed point in accordance to the design parameter tau. This fact becomes particularly important when the bandwidth demand is very severe. That is when we must have very broadband antennas, so to speak. So now we have other issues or other kind of antennas that have been used, and this you might find them in mobile phones and so forth. I don't know whether anyone has been courageous enough to open their mobile phone, okay? Or you just, it gets messed, you take it to River Road. So these are called fractal antennas, and the beauty with the fractal antennas is that they are space filling. That is, we can make antennas of infinite length by just making sure that we repeat the structure itself, even to the microscopic level. And this, therefore, fractal antennas are characterized by a repeating antenna structure as we zoom into the structure. And this has been informed by nature, because many times if you look at, say, a cypress leaf, I don't know whether you know what cypress tree. Anyone seen a cypress tree? Yeah, you don't know what cypress tree is.
Personally, I've never seen a cypress tree.
You have never seen?
Yes.
I'm sure even in your area of residence, you must have seen it. Now, next time you are out there in nature, just look at some of the leaves, and you can see some of the leaves, if you looked at them, when you look at them from afar, they have the same shape. And as you go closer, they have other structures which look like the leaf as well. Okay? And this is what we are talking about, the fractal antenna. That is, if we have a triangle on the broad end, as we zoom into the antenna itself, we'll still see the same triangle, but a smaller one, so to speak. Okay? So this have been inspired by nature to give infinitely electrically large radiating structures in a space-filling way. And therefore, we can fit an antenna that can work at multiple resonant frequencies, especially for the modern mobile phone, which has very many radios. So, like, for those of us who don't have a Mulipamwizi alone, but we have a smartphone, we'll have a radio that will be operating in the Bluetooth at about 2.45 or gigahertz. Then we have another one which would be operating the Wi-Fi, okay, and so forth, and also the one for the GSM and so forth. Those radios will be operating at their frequencies. But then, if you have to have many radios in that phone, then you must have as many antennas as you have the radios. But now, you can implement the resonant frequencies with just a single antenna by going into the fractal form of that antenna. So they are characterized by radiation at multiple resonance frequencies, therefore giving a multi-band antenna useful in modern communication systems. So the common structures will include, one, what we call the core fractal. Okay, I'll show the picture of this, the Sierpinski gasket and a carpet fractal as well. We have what we would call the Minkowski fractal, which can have many different kind of shapes, pentagon, square, and so forth. Then we have these examples here. So the Sierpinski gasket is first of all an equilateral triangle. These are called patch antennas. So you have an equilateral triangle. Then you get at a triangle now that is a third of the first triangle, and you cut that out from the center of the main triangle. Then from that one, you can get a third of it again, and then on all the third triangles remaining, you cut it out. And therefore, if you look at the main antenna from the top, and as you zoom closer and closer, the same structure repeats. That is a big triangle in the center, surrounded by several smaller three triangles behind. And the black side, of course, is the conducting metal, which will be forming which will form the antenna itself. So such an antenna has several resonant frequencies, and it's usually very important. So this pattern here is usually called the generating pattern, and then the smaller one, as you go closer and closer into smaller and smaller values, you get what we would call the generating function, and you can make as large an antenna as you like, because even with this we have only 3 iterations. We can go to the 4th iteration by putting in now we cut out the center of this particular triangle on each of them, and then repeat the others in between. The Sierpinski carpet, this looks almost like the carpets that we get in the houses, and therefore it's a square one, this one, where we have a big square cut out from the patch, and then smaller ones cut around it. Then those ones also have their small ones cut around them, and so forth. Okay, and this will become a very good antenna to radiate at different frequencies. The Minkowski fractal is where we have a square. Then we rotate it about 45 degrees. Then we cut it out from the center of the patch, and we continue rotating them until we get to the final value of the final whatever iteration we can go to. Okay, so the main antenna will cover that space, but all the other resonant frequencies will just be within that that space that you already started with. And therefore we can say that we are using the space that we have set out for the antenna maximally. Another one is what we call the Koch loop, where we are having a loop, and then on each of the straight edges, a third of the way, we make we add an extra length that is a third on both sides, that is a third on both sides like that, and we continue doing that until we have the biggest of the desired iteration. The other one would be the patch, where we have, this would be made of a wire, and now this one we have the patch itself, which is just a flat conductor in which the edges have been made to follow the Koch kind of, the Koch fractal. And this would be the conductor, but then we want to use the aperture as the radiation surface, but now the edges of the aperture have been made to have the Koch structure. So these are some of the antennas that you see, and now I'll show you how a dipole would look like, a Koch dipole would look like. I don't know whether you'll be able to see this. Let me see. I'm going to show this one as well. So I'll stop presenting for now and present something else. So present a window, and I want to show that. So I don't know whether you can see that. Can you see that? Now, this is how a dipole antenna would look like. That is, we have the normal dipole, which is a straight length of wire. And then we apply on every side, we put an equilateral triangle. If you look at that edge there, you see this is an equilateral triangle. That is, we have added a third length onto the half length that we started with, and we have put that there. Then on each straight edge, we add another half length. So we have this other one, which is a third of the length from there to there, and that is the length from there to there. We have a third, and so forth for all the straight lines until you can go no more, so to speak. Because at the end of it all, the realization, the practical realization will determine how much of the iterations you can do. And this will have resonant frequencies at different frequencies, because for each of them, it will be different. I'm sure for those of us who have a radio, we have like a whip antenna that is usually you pull it out, or you push, or you shorten it, and then you get better reception when you are using the radio. All you are doing is to tune the length of that monopole to the radiation, to the station, to the frequency or the wavelength of the station that you are trying to receive. Okay, so that's another way of dealing with it. That is, we can vary the length, or we can just have the length already done, and the frequency does that for us. So that gives us, or brings us to the end of that talk about the antennas. That is the antenna types that we have there, and I'm sure you have a fair glimpse of how you, if you are to design an antenna, you know what kind of values or what kind of things you have to deal with. Like I said before, nowadays, design of antennas has been simplified because we have very many simulation packages, and most of the times, in fact, for many people, they don't need even to know how to solve the Maxwell's equations. All you have to do is to cut a wire, or to put a structure into the workspace of the simulation software, simulate it. It doesn't do what you like, you tweak the shape or something like that, or you try to optimize, and voila, you have a good radiating antenna. And many people have even patented this without having to solve a single Maxwell's equation. But at our age, of course, what we are trying to do is to make sure that you be the ones to create the simulation packages. Don't be people who will be just using the simulation packages that have been made, or even if you use the simulation package, you know what you need to do when you do an optimization. That is, you direct the optimization of the software to what you really desire. Okay, so I hope that one is good enough for you. So you are going to be covering this later when you deal with in the 5th year. For those of us who will be dealing with antennas in the 5th year communication system, that is the microwave circuits and systems. But for us, that was an introduction of the antennas themselves and what we have there. So any question before I continue?
No question.
No question. So then I'll show you now what we want to do is to look at some other things. Now we have looked at radiation. We have seen that we want to maximize our system to radiate as efficiently as possible. But then it's not always nice to have a radiator, especially if you are talking to your significant other somewhere on phone, and another one is speaking to theirs, and then the two radios start interfering with each other. Of course, you won't be very amused. And therefore, we want to look at what we call electromagnetic compatibility of systems. When you go to the 5th year, of course, you'll be given projects to work on. Some of these will be radiating functions, or you can get a very good function, but then it will start to interfere with other people who are next to you or something like that, and that would be an issue. For many of us, we have gone to banks and we have seen some of them, they post notices saying that please switch off your phones. If you go to visit a place like, say, KPLC, where they store the fuel, they'll tell you you cannot go in there with a metallic system, even a watch, or even a telephone. You have to leave it at the office before you can go into the fuel area, because the radiation coming from your radios can actually ignite the fumes. Other places that you get problems like this is where if you go to a place like a portion mill, or places like working with people like Unga and the like, most of the time the air will be full of gray or whatever flour particles, and this can also be ionized or polarized by the radiation that is coming from your system, and most of the time they can create a spark and they can explode as well. So what is electromagnetic compatibility then? So electromagnetic compatibility, or in short EMC, has become a mandatory requirement for the electronic equipment, especially now that we have a crowded spectrum. So in the past, the EMC was referred to a variety of guidelines that were used in the industry to describe the radiated influence or the susceptibility of an electrical or electronic appliance in an increasingly rich electronic environment. And each country will have always had their own requirements with a body that would be regulating that. In Kenya, of course, you know, we have the CA, or the Communication Authority of Kenya, that deals with that. So in 1996, the European countries issued an EMC directive called the 89336 stroke EEC, or IEC 801, where IEC stands for the International Electrotechnical Commission, and this was made binding for the first time. Before, it was done voluntarily, but now it was made binding that everyone must adhere to those guidelines. So EMC describes the ability of an electrical piece of equipment or appliance to function satisfactorily in its electromagnetic environment without affecting other equipment in this environment or itself becoming affected. Okay. 2, the manufacturers of electrical and electronic equipment must declare that the equipment conforms to the protective objectives of the EMC directive, and this will be done through a mark that is written CE. If you open any of your systems that you have, let's say, for example, if you look at your phone when you just buy it, if you didn't buy it off the eBay and the likes, it will always have a sticker with a CE mark on it. This is more like the one we have for cabs and the likes, but now CE is for conformité with the pen. This is to show that it conforms with the EMC guidelines from the IEC 801. Okay, and all of them, even with us, we usually have to have this mark because Kenya is a member of IEC. Okay, and the representing organization in Kenya is called the Kenya National Committee for the IEC. So when the CE mark does not give a full technical qualification for that particular equipment, it will indicate that the device meets the fundamental requirements for the environmental and safety in Europe. The manufacturer must take full responsibility vis-a-vis their customers, the consumers, for observing that the relevant emission limits and interference immunity requirements have been adhered to. So since its introduction, the EMC directive, that is 89/336/EEC, has had a sweeping effect on the design of electronic products worldwide, so to speak. And interference immunity requirements are particularly important for, say, equipment operators, the people who will be operating the equipment. You don't want radiation to come into you, or you don't want to interfere with other people's actions and so forth. And 2, installations. And 3, we have what we call the systems themselves. That is a system of electrical equipment that could be causing or interfering with others. And then the correct functioning is ensured only if we have taken sufficient EMC measures from the start. So constant functionality will imply high availability of the installations and systems, and hence a higher performance figure for a cost-effective operation of that equipment. By high availability means that your equipment is not dead most of the time because it's being interfered with, but it's using, you are able to operate it throughout the period you want to operate it. Two, electromagnetic interference is part of the EMC. But what does it mean then? This will refer to the unwanted signals in devices or systems that will make operation of that equipment difficult or impossible. A system that is not EMI compatible will have what we call an EMI problem. This is particularly important in computing systems, especially where we are running clocks at ever higher frequencies, many of them going at around 3 gigahertz and the like. And this can have frequencies, say, for example, the third harmonic for that would be about 9 gigahertz. Another one will be at 27 gigahertz. And if these are high enough, that is, they are strong enough, they will cause interference outside because they'll be radiated very easily out of your board. So an EMI signal must have a source and also a coupling path to the disturbed or what we call the victim equipment. So, and hence, if we remove the source or we remove the coupling path, then we will solve the EMI problem of that particular system. So the interfering signal path need not be conductive medium, because in many cases we can say that the coupling mechanism will consist of both radiation and conduction. So one method of alleviating an EMI problem is to keep the source strengths across the coupling path below the appropriate levels, and these appropriate levels will be defined in the EMC standards. That is, you should not be radiating so many dB above a given reference at a given frequency, so to speak. And that will be given there as a standard for you to adhere to. And you have to make sure that your system does just that or far below it. Okay? So the pertinent levels will be covered in the EMC, have been covered in the EMC directive, and the IEC 801 will be applicable to one, an equipment that can emit disturbance signals or devices that are sensitive to those disturbances from electromagnetic energy, such as portable tools, computer peripherals, and industrial equipment. In the early days when you are watching TV, if you started a kitchen blender, that is, you are trying to blend, you want to make orange juice or purple juice and the likes, and your younger brother was watching TV, he would start screaming because lines will start forming on the image because of interference from the blender. That would be the interference conducted through the power cables that are connected in the system, because many of the wiring system in the house is connected, especially for the sockets. They are connected in a ring, so to speak. So IEC guidelines do not necessarily cover radio and telecommunication equipment. And to minimize EMI, one must first determine whether the system will be operating at high or low frequencies. So for EMC purposes, a system will be said to operate at low frequencies if all the transmission lines present in the system have lengths that are shorter than 1/10 of the shortest wavelength of the signals that it will be processing. So suppose the magnitude of a current flowing from a source to a load changes at some instant of time. That is, we have a sudden change of the current, and therefore we'll be introducing some transients. So if L is the length of the signal path, and this change is not noticeable within a time t equal to L by V, where we see this is the time of flight, and V is the phase velocity along that path, the system will then be said to be a low frequency circuit. So the small slow perturbations in currents will be referred to as quasi-static phenomena, and a low frequency circuit can therefore be modeled with an RLC circuit. So additional phenomena may arise in high frequency systems which are no longer negligible, so to speak. And this will include propagation delays, Two, we have radiation itself, and the scope. We can show the scope of the EMC will then be illustrated as shown. That is, we have the electromagnetic compatibility of the system, that is the apex. Then we have an emission source, so we'll have electromagnetic emission. We can have conducted emission or radiated emission. Then we could have the victims or the susceptibility. That is your system susceptible? Say, for example, if you are wearing a pacemaker, you will find that many of the times you will be advised not to be near where a car repair shop, because when the spark plugs discharge, of course, they generate high frequency signals which can interfere with your pacemaker. So here we have electromagnetic susceptibility, and this can be conducted or radiated as well. And those form the components of EMI. So EMC will therefore cover both electromagnetic emission and electromagnetic susceptibility. And emission will apply in the case of an EMI source, while susceptibility will be applying to the victim and can be classified under one, conducted emission in the form of interference currents or voltages, or radiated emission, either as electric or magnetic fields near the source or the electromagnetic fields farther away. So for cost-effective solutions, because trying to mitigate problems caused by EMI and EMC issues are very costly, and therefore you want to give a cost-effective solution, and all phenomena must be considered, and EMC components for EMI suppression installed either in the source or in the victim. That is, we can protect the system that we want, that is a victim, or we can try to suppress those the source of the EMI. So an EMI source is described as an electrical equipment that will emit EMI, and examples will include the following. For the discrete spectrum radiation, we have the microprocessor or the microcontroller systems, and most of us nowadays are so fond of dealing with microcontrollers, with Arduino and the likes, and we create functions that may be very nice, but if we were to subject them to an EMI investigation, the CA of Kenya may not allow us to sell that product. Okay, so when you are creating your projects, you have to make sure that you also know how much of the EMI it will produce, because when you make an application or a system, then you want to sell it, you want to make bread out of it, but then will you be allowed to sell it? So we have other things like RF generators, they are resonant. We have medical equipment, data processing systems, which will be connected to the microprocessor systems as well. We have microwave equipment, ultrasonic equipment, where this is ultrasound that we cannot hear, about 20 kilohertz and the like. We have radio and TV receivers, which are now becoming digital as well. We have switched mode power supplies, which are given in almost every system today to try and reduce the weight of the power system. We have the uninterruptible power systems, or the UPS, that you have with many computers. And two, we have the electronic ballast in gas discharge lamps, okay, which many times are switched at about 20 kilohertz, or about 20 kilohertz, to try and turn the lamp on and off, the discharge, to reduce the flame in the lights. Then we have what we call the continuous spectrum, that is, they radiate at all frequencies. Okay, this will be radiating at different discrete frequencies that will radiate at all frequencies. One is a switch gear, such as relays, and this would be contactors and relays that you'll get in an industrial system. We have household appliances, such as the blender we've been talking about. It has, some of them will have brushed DC whatever motors and the likes. We have the gas discharge lamp, which is ubiquitous in all homes today. Then we have the power supplies, the battery chargers that we have, and frequency converters and welding machines, as well as motors that have brushes, that is commutator, and the oscillating drives, as well as what we would get whenever we have a thunderstorm. We will get lightning, and lightning is a flash that will come, and this is what we call the atmospheric discharge, and it will generate very many frequency components that are, of all sorts of frequencies throughout the discharge value itself, because usually they are short pulses, so to speak. So EMI sources may be classified under two groups. One, we have sources with discrete spectra, that is high frequency oscillators, and microprocessor systems that are generating narrowband interference, that is low energy sine waves. And two, we have sources with continuous spectra, such as switchgear and electric motors, in particular, commutated DC motors in household appliances, which would be generating broadband interference, that is, its pulses that in time duration are very short. And you know that the Schwartz, Wiener Schwartz kind of, whatever, it's called Wiener Kirchheim, yeah, it's a Wiener Kirchheim condition in signal processing, where we have the Schwartz inequality. I'm confusing you guys. It's the Schwartz inequality where we have the inverse relationship between time duration and frequency content of a given signal. The shorter, the sharper the pulse in time, the broader the frequencies that it contains. And this can be proven using the Fourier transform. So the victims themselves are electrical devices, equipment, or systems that are subjected to interference and which may be affected by it. And victims can be separated as well into two groups. One, victims with a narrow band or discrete spectra. Two, victims with broadband or continuous spectra. So some of the victims that we can see here are, for those the discrete spectra, we have the radio and TV receivers, the modems that you have, that is modulation, demodulation systems. Then we have the data transmission systems, because especially if you are using the digital transmission of before. Then we have the radio transmission equipment, remote control equipment in the house, microwave equipment such as the microwave oven. We have the cordless or cellular phones that we are now having in every pocket. And two, continuous spectrum, we have the digital and analog systems such as your amplifier and radios in the house. We have data processing systems again, and process control of computers in industry, and control systems, video transmission systems, frequency converters, as well as interfaces. So interference voltages and currents may be grouped into one, common mode interference. That is, we have two values the same, the two lines are affected the same way. And then we have what we have a differential mode interference. We then have asymmetrical interference, and these three types are shown below. If you have a twin wire transmission line and say lightning strikes, the lightning will strike both of them at the same time, and therefore we can expect that any interference will be the same in the two lines. And therefore, between that and the common mode, that is and the ground, we have a common mode voltage, VCM. Then we have a differential mode where only one of them is affected, and therefore is the interference between one line and the other. Then we can have what we would call the unsymmetrical interference, where we are just looking at the two of them are interfered with different voltages, V1 and V2. So common mode interference is mainly a high frequency system. I hope I'm still in class.
Yes, it's still in class.
Yeah, because I was running short of charge and I nearly thought I had left the room. So the common mode interference is mainly a high frequency phenomenon, usually above 1 megahertz. and occurs between all lines in a cable and the reference potential. So consider a two-conductor transmission line with the conductors at potentials V1 and V2 respectively. So the common mode potential on the line is then defined as the average voltage, okay, on the lines less the reference value. That is, if this is the reference values and it's ground, then VCN is just V1 plus V2 over 2. If you recall your analog electronics from third year, you dealt with the differential amplifier, and you are told the beauty of the differential amplifier is because it rejects the common mode signal while amplifying the differential signal. Anyone can recall this?
Yes.
So when you are driving a two-wire transmission line, we usually call them balanced lines. And this is the way you'd be, say, for example, feeding a dipole, okay? And a dipole antenna, you feed it with a balanced line. And therefore, you want to drive it with a differential amplifier first so that you can always reject the common mode signal, which would be the, the interference signal, because most of the time when the antenna is struck by atmospheric discharge, it will be struck equally on both lines, and therefore the signal that will be generated will be common mode. So there are no common mode currents when the medium surrounding the conductors is actually lossless. 2, we have the differential mode interference that will occur symmetrically between two lines, and is primarily a low frequency that is below a few hundred kilohertz phenomenon. So for a two-conductor transmission line with conductors at V1 and V2, where you have one is, say, the return and the other one is the send, then the differential mode potential will be defined as VDM equal to the voltage on one line less the voltage on the other. And therefore, if you have a common signal between on the two lines, that will be subtracted out. So asymmetrical interference describes the interference between one line and the reference potential. So differential radiation current are a natural consequence of the physical layout of your circuit. So different PCB tracks, that is the traces that you make when you are etching your signal or your circuit, will be carrying different current densities and will have a differential mode current that will lead to an H field radiation, that is, will be radiating magnetic fields. 2, it will have a common mode radiation current, which will lead to electric field radiation because of the capacitive coupling between the two PCB tracks. And the interference can then be classified in terms of 1, the mode of propagation, 2, the coupling mechanism, that is from the victim or from the aggressor to the victim. 2, and propagation will be mainly in terms of conduction over conductive structures at low frequencies. That is, at low frequencies, most of the propagation of the interference signal will be through the conductors. Hence, conductive interference will be primarily a differential mode kind of currents or voltages at frequencies below a few hundred kilohertz. So propagation is only by means of EM radiation at higher frequencies, and therefore if you create your, say, digital circuit, you may find that when you look at the Kanu map and so forth, whatever tool you use to design that circuit, you can see all the gates, all the functions should work as intended. But when you etch it or when you imply or implement it on hardware, you find that it does not work. That is, the signal is not passing through the gates, but it's getting to the output somehow directly without processing. This is usually because of radiation from a direct connection between the input signal and the output side of your circuit. And this is what we are calling radiation from at high frequencies. So at these frequencies, the term coupling will be used to describe the interference phenomenon in the megahertz and higher ranges. So interference at high frequencies will then be primarily a common mode phenomenon and will be increasing with increasing frequency because the length or the dimensions of your circuit will become more and more comparable to the wavelength as the frequency, operating frequency increases. And we have seen from the antenna theory that when the length or the dimensions of your circuit are of the same order of the wavelength, then they become very efficient emitters or radiators of electromagnetic fields. So this is because the coupling factor and the effects of parasitic capacitances between the lines and inductance between the conductors will be increasing in frequency as well. So a general EMI environment will be as shown below. Here we have the circuit that we have just created in the lab. This is the function we are designing and we want to sell. Now, what would happen is that it will input an interference current and an interference voltage to the measurement that is from the power supply. So the line impedance, this is called a line impedance stabilization network. It's supposed to stabilize that power so that nothing goes to, that is, the power supply does not feed any interference to the source, and therefore you can measure how much of the interference voltage or current you have with your measurement system, which is usually a spectrum analyzer or a storage oscilloscope if you want to see the waveforms. Then it could radiate. It could be by radiator. Now, this one is to take care of, to measure how much of the conduction interference you have through the power supply lines. And here, how much does it radiate at low frequencies, or that is at the common mode kind of values, that is the the electric fields. And therefore you have, say, an antenna here and your measurement receiver there, which could be also a spectrum analyzer or a radio receiver. Then it could be radiating electromagnetic waves, and therefore you will use a loop antenna to do that. This you can use a dipole antenna. Here you use a loop antenna and a measurement. And then here we have interference, and this will be direct interference, and this can be measured in a dipole antenna. And CAK is what they'll be doing when they are going around the town trying to find out who are radiating illegal or who are operating illegal radios and the likes. They'll be walking around, or they'll be driving around with a vehicle with a broadband with an antenna dipole to try and receive that radiation field from the others. So since interference signals can be either conducted or radiated, the propagation along these paths can be detected by measuring interference current and voltages. And this, rather than continue from here, I think my time is now up. We will continue from there tomorrow and look at the measurement of the interference for electromagnetic compatibility. So now I'm open for any question that you may have right now. And if not, no question is forehand, then we can talk about this stuff tomorrow as we continue. So we are nearing the end of the course. The only other things that I have left are, say, for example, things like the standards and standardization. Then we'll have things like the insulation properties, that is liquid and solid. Last semester we dealt with gas. And then there is the Kenya National Committee for the IEC is trying to organize a webinar on standards and standardization. So very soon I'll be putting up a class. I'll set up a class for you to register into. That is those ones who are interested. It's not a must that we all have to come to the class, but it's a very nice thing for you to learn, because many times you can even have your industrial attachment at KEBS, and you can you'll be getting very nice first-hand kind of information from the people dealing with standards. So I'll communicate with you when I get the dates and when we can start registering, so that we can listen to this. Usually, this class has been unfortunate. I always organize an industrial visit. Usually we'll meet we'll go to a manufacturing plant or a standardization plant, like that is a standards regulator like KEBS, to try and see what they do in what is done in the industry, to try and bring us, to put our feet down on the ground to see the necessity of studying what we are studying in electrical engineering. But this class is unfortunate because of the COVID guy, and maybe we may, when the things ease out, we may get a chance to go out, but not very, I would promise for now. So with that, if you have any question, you can ask, or we can then call it a day until tomorrow.
Dr. Mwema?
Yes?
I noticed something in my room.
Hello?
Hello, can you hear me?
Yeah.
When I put my laptop on the same extension as my radio would get poor reception. Is that also part of EMI?
Yeah, that would be part of the interference as well. Maybe your computer is running on digital power supplies, switched mode.
Yeah.
And maybe what is happening is that it's conducting a lot of whatever, there's conduction into the radio, or you are radiating a lot from your computer. So the radio is trying to receive that. But I don't see how. Well, most of the time the laptops are usually very well made. They are made with the electromagnetic interference in mind, and most of them must. If you look at their labels, you'll find that they are all. They'll have something like, what you call it. They'll have that CE mark to show that they are compatible. But unless your computer is old and therefore it's radiating stuff, I don't know. That could be an issue. Like, I don't know whether any of you can hear mine. Mine has a problem with the fan. It's always making a lot of noise. And fans on themselves, of course, they'll be running on a DC motor as well, and they could also be radiating. Most of the times, maybe, have you opened it?
No.
Yeah, because if you opened it, you'll find that the processor is usually protected with a conducting metal plate with quite a few holes around it. But what I can say in all is that you are getting interference because your computer has a Bluetooth radio. It has, maybe you have a modem there also as well. The wireless one is there if you are using wireless, wireless internet and so forth. So this could be the cause of it. But without seeing it, I can't really diagnose it. It's more like a patient talking to a doctor on the telephone line.
Okay.
Yeah. So any other practical issues we have come up with or we have noticed? Okay, since we are all silent, then we can call it a day. Let's meet tomorrow and continue with the discussion.
Yeah, thank you. Have a good day.
Yeah, a good day too.
Oh, and there are also some questions that were posted on the comments of the PDF.
I think I saw are they two from you, isn't it?
Yes.
I thought I addressed it. One of them is that when you are studying, you didn't actually notice that I had indicated that we are considering a line of unit width.
Yes,
And,
that one
and
I
that's
had
why we'll
seen.
have we are just integrating only over the y dimension rather than also the x direction. And in any
Yes,
case, if we
that
were to
one I had.
multiply, we were to integrate over the x dimension, we just multiply by w, or the width of the line, because we said that there's no variation of the field in that direction, isn't it?
Yes.
Yeah, so you just multiply it by the width of the line. The other one was something about what? I don't know. I can't get it offhand. You may remind me now.
There was two more I had asked on one of the examples you had done about there was somewhere where we were differentiating with respect to y, but still changing a cosine to a sine. In one of the examples.
If
Oh,
that could be just a typo, because most of the time what I do is that to try and ease the work I have in trying to to type, I'll just cut what I've already done and post it on the other line. And maybe what happened there is that I forgot to change that it's the y one I'm differentiating. But most of the time you'll find that if we have a cosine multiplication, say for example TM modes will have sine mode, that is sine m pi by multiplied by m pi multiplied by x by a, and sine n pi multiplied by y by a, isn't it?
yes.
So sometimes when I differentiate, I could differentiate and leave the cosine as a cosine, as the sine as a cosine in the x direction, while I needed to differentiate the y direction. I'll have to look at that. I'll check again and see the particular question you're asking. Then I can see whether that is actually a typographical error or that is the way it should be.
Oh, okay.
Or you can tell me which example you exactly mean. But when you go through the examples themselves, usually if the argument you follow is sound and you see such kind of problems, you can actually tell straight away that that is an error.
Oh.
Okay, that's how you gauge how well you're understanding. I don't want you people to cram my solutions. Try to solve to get the solutions yourselves. If you can't get them, try to look at it again. Then you can raise the issue. Then I will relook, and then I can discover whether there was an error or it was okay, so to speak. And you are the ones who are not following the correct argument. I think that's how we should learn by when we are trying to learn this electromagnetic, the electrodynamics. And if you don't, you should try to make sure you practice a lot, because it's only through practice that you can see that they are all repeating. And when you solve a problem and you see a grievously different pattern, you will already know that there is a problem, either in this problem solution or in the actual whatever posing of the problem. Okay? At our age, we start learning by patterns rather than by getting new stuff. We are forming patterns, so to speak, and your brain will work faster when you are trying to recognize patterns.
Okay.
So, okay, with that, then we can call it a day. Do have a nice day, and let's meet tomorrow then.